All right, let's dive right into this explainer. Today, we're exploring the seriously fascinating world of bioprocess engineering. Now, I know that might sound like a dense, heavily technical term, but as you'll see, it's actually incredibly intuitive. We're essentially going to learn how to build and manage factories on a truly microscopic scale. We're taking the rigid, math-heavy world of engineering and mashing it up with the messy, living world of biology. Just imagine shrinking an entire industrial manufacturing plant down to the size of a single microbe. It's pretty wild.
So here's a question to get us started. How do you actually manufacture life-saving medicine using an invisible workforce? I mean, it sounds totally like science fiction, right? But literally every single day, the antibiotics you take when you're sick, the enzymes in your laundry detergent, and even the organic acids used to process your food are manufactured not by heavy machinery, but by living cells. But how do we control them? How do we make absolutely sure they do exactly what we need them to do? Let's unpack this mystery together. Section 1. Meet your microscopic workers, cells as tiny factories. Okay, so what exactly is bioprocess engineering? Simply put, it's the science of combining biology and engineering to design, build, and run microscopic factories using living cells as the workers. You see, biologists understand exactly how the cell works, how it replicates, and what it needs to survive. But engineers, they know how to scale things up, how to control temperatures, and how to manage fluid dynamics. This entire field literally only exists because these two distinct groups have to team up to keep our invisible workforce organized, happy, and immensely productive. It's really the ultimate interdisciplinary partnership. Moving on to Section 2, inside the bioreactor factory, creating the perfect environment. If you've ever heard the term bioreactor, it can definitely sound a bit intimidating, but honestly, it's just a highly controlled environment. Think of it like a high-tech hot tub, or maybe a massive automated cafeteria and workspace combined into one. Our microbial workers are extremely picky. If they get too hot, they die. If they run out of air, they stop working entirely. The bioreactor is the physical vessel designed to keep them perfectly warm, constantly stirred, and comfortably breathing, so they can focus all their energy on manufacturing our desired product. Let's break down the machinery of a classic continuous stirred tank fermenter. Right at the center, you've got the impeller, which is basically a giant stirring spoon on a motor, making sure the cells are evenly mixed. Next up is the Sparger, a pipe with tiny holes at the bottom that acts as an oxygen bubbler so the cells can breathe. Then we have the cooling jacket. As cells work and multiply, they actually generate a ton of heat. So this water-filled jacket regulates their temperature to keep things nice and comfortable. Baffles are these metal strips on the walls that prevent the liquid from just swirling around in a dizzying, useless vortex. And finally, the feed ports, which are basically the tubes we use to deliver their food. It's an incredibly elegant, perfectly tuned system. Now, despite all that complex machinery, the actual step-by-step life cycle of what we call a batch culture is beautifully straightforward. Step 1, we sterilize the tank with steam to kill any rogue bacteria. We only want our specific workers inside. Step 2, we add our chosen worker cells. Step 3, we feed them a nutrient-rich broth. And step 4, after they've multiplied and done their job, we harvest the final product, whether that's the cells themselves or a specific chemical they've released. It's a surprisingly simple biological life cycle happening inside a highly complex piece of engineering. Section 3. Feeding the cellular workforce, the microscopic buffet. Just like humans, cells are highly motivated by food. We're establishing an absolute fundamental rule of our factory here. In engineering terms, we actually call the cell's food substrate, and substrate equals energy and growth. The rule is super simple. The more the cells eat, the more they multiply. And in a bioreactor, a larger workforce obviously means a higher output of whatever product we're trying to manufacture. The substrate is the fuel for our entire operation. Think about a poorly stocked cafeteria versus a sprawling, well-stocked one. In a low food environment, the cells are desperately searching for nutrients. They eat slowly, their growth is sluggish, and our factory's production practically crawls to a halt. But flip that around. In a high food environment, nutrients are absolutely everywhere. The cells eat rapidly, the workforce multiplies incredibly quickly, and production just booms. The concentration of food directly dictates the speed of our operation. It's all about keeping that buffet fully stocked. Section 4. The speed limit of growth. Decoding the monod equation. Let's get into the core of how this works. So we're talking about the biological speed limit. Now, common sense might tell you that if more food equals more growth, then infinite food should equal infinite growth, right? Well, living things just don't work that way. Cells have a physical maximum capacity. There is an absolute fastest rate at which a cell can consume substrate and divide. Once they hit that top speed, it literally does not matter how much extra food you shove into the bioreactor tank, they physically cannot grow any faster. Their internal gears are spinning as fast as biology allows.
This concept perfectly translates the math of the Monod equation for us completely without needing a single formula. Think about the growth speed compared to the available food. When we provide just a little bit of food, the growth speed is at, let's say, 25. Give them more food and boom, the speed jumps to 75. But here's the real kicker. When we provide an endless buffet, an absolute overload of nutrients, the growth speed hits 100 and completely stops rising. That 100, that's our biological speed limit. The cell's internal machinery is completely saturated at that point. You can keep pouring food in all day, but the growth speed remains totally flat at 100.
And you know, this is exactly why bioprocess engineers care so much about this rule. Substrate, the food we feed these cells, is often very, very expensive. The Monod model mathematically dictates how to run our bioreactors efficiently without wasting any food, perfectly balancing the buffet with the cellular speed limit. Engineers can precisely calculate exactly how much food to pump into the tank to keep the cells at their absolute top speed, without dumping in extra food that will just sit there unused. It's the ultimate tool for maximizing factory efficiency and keeping those costs down.
Section 5. Why bioprocessing matters today. Real-world microfactories.
To put this into perspective, a massive 40% of common bioreactor production represents antibiotics and medicines. From the early days of mass-producing penicillin to modern cutting-edge biopharmaceuticals, these cellular workers are quite literally the backbone of modern medicine. Another 30% goes to industrial enzymes. We're talking things like the rennet used in cheese manufacturing or the active enzymes for your laundry detergents. We also have organic acids like citric acid and even biofuels. Everyday items you rely on, from the food in your fridge to the fuel in your car, are entirely dependent on these controlled microscopic factories. It's everywhere.
And you know, just as human factories look completely different depending on whether they're building cars or computer chips, bioreactors vary based on the specific worker. We've talked mostly about the continuous stirred tank, which is the standard workhorse industrial mixer. But what if your cells are just too fragile for a harsh spinning impeller? Well, you'd use an airlift fermenter, which uses very gentle gas bubbling to mix the fluid. If your workers are algae that actually need light, you'd use a photobioreactor made of clear glass tubes to capture solar power. Or for a fluidized bed, you attach the cells to solid particles and let a fluid stream flow over them. The engineering always has to adapt to the biology. So it leaves us with this incredible thought. If we can engineer cells to produce almost anything in these highly controlled tanks, carefully balancing their speed limits and perfectly optimizing their environments, what on earth will our microscopic factories build next? From lab-grown tissues to completely novel sustainable chemicals, the future of manufacturing is undeniably microscopic. Thanks so much for exploring this explainer with me today. I really hope this helped illuminate just how beautifully biology and engineering seamlessly intertwine.